Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. Hello and welcome to part 3 in our series on multiple regression. Now, I am going to assume you watched parts 1 and 2 of this series, or you come to this video with that knowledge already in your head. So if you need to, go back, watch those 2 videos, and then come back to this one. Otherwise, you may end up watching this one and become confused and frustrated, and neither of us want that to happen. So here in part 3, we're going to talk about building regression models. So we will do that by introducing our independent variables into the model one at a time, then we'll add them 2 at a time, and then in this case, we'll add all 3, and then we'll see the models that come out of that process, and then make a judgment call on which model is best. So we'll talk about all that criteria as far as determining the best model as we go forward. So all that being said, let's go ahead and get started. So as we discussed in parts 1 and 2, conducting a multiple regression analysis requires a fair amount of pre-work before actually running the numbers in your software. So here are those steps real quickly. We generate a list of potential variables, so independence and the dependent variable. We collect data on those variables. We check the relationships between each independent variable and the dependent variable using scatter plots and correlations. So here, we want to see which independent variables are actually related to the dependent variable in the first place, because the ones that are not are probably going to be left out of the analysis. Then we'll check the relationships among the independent variables themselves using scatter plots and correlations. So here we're checking for multicollinearity. And then, usually optional, but I do it anyway, and that is conduct simple linear regressions for each independent variable, dependent variable pair. And that's what we will do in this video, because here we want to learn how to build models up and then tear them down to find the best one. Then we'll use the non-redundant independent variables in the analysis to find the best fitting model. And finally, most likely in a later video, we'll use the best fitting model to make predictions about the dependent variable. And we'll talk about confidence intervals and prediction intervals at that point. So remember, you are a small business owner that runs a delivery service, like a courier service. You do same-day deliveries of packages, letters, small cargo, etc. And you want to be able to predict the total travel time for each trip. So on a trip, you may have several deliveries. They may be close to your office, they may be far away, etc. So you go back and look at 10 past trips and record 4 pieces of information: the total miles traveled for that trip, the number of deliveries during that trip, the daily gas price, and finally the total travel time in hours, which is your dependent variable, or the thing you're interested in predicting. So here's the data. We have miles traveled, that's our first independent variable, x1, number of deliveries during the trip, that's x2, and the gas price that day, that's x3, and then our dependent variable, travel time, is why they're on the right. So remember, it's always a good idea to visualize the relationships. So we have our travel time dependent variable, then we have 3 independent variables. So we have miles traveled, number of deliveries, and gas price. And of course, all 3 of those have some relationship to the dependent variable. We don't know that yet, but we will. But we also have to account for the relationships among the independent variables themselves, which are there in the dashed line. So we have 6 relationships we have to analyze and keep in mind as we do our analysis. Let's quickly review the scatter plots comparing the dependent variable and the independent variables individually. So the first scatter plot, we have our travel time dependent variable versus our miles traveled, our first independent variable. And as you can see there, we have a strong linear relationship. Starts at the lower left of the graph and goes to the upper right. We have a correlation coefficient of 0.928. That's very, very high. We have a p-value for the correlation of 0.000, which means it's less than 0.001. So we know that that variable, miles traveled, is related, strongly related to our dependent variable, travel time. So we'll put a green check there. The second independent variable, number of deliveries, x2, that's also very strongly related. So the line starts in the lower left, goes to the upper right. They fall along a rough line there. The correlation is 0.916, again, very high. The p-value is less than 0.001, so that is significant. So we'll put a green check there. So our first 2 independent variables do have strong linear relationships, very strong correlations with our dependent variable, which is good. Now our third independent variable, gas price, does not. As you can see, the data points do not form any pattern. They're kind of all over the place. And we can see that in the correlation. It's 0.267 with a p-value of 0.455. That is not significant, so we'll put a red X there. So gas price X3 does not have any sort of linear relationship to the dependent variable right off the bat. So usually we would just go ahead and remove that from the model, because if it doesn't have one to begin with, it's not going to contribute anything to the regression. But of course, for now, we're going to leave it in and see how it affects our numbers as we go forward. So now we have the scatter plots for the independent variable comparisons. So again, we're looking for multicollinearity. So the first scatter plot, we have miles traveled versus number of deliveries, and here we have a problem. So our first 2 independent variables have a very, very high correlation of 0.956, a p-value less than 0.001, and I'll put a skull and crossbones there because this is a problem. 2 independent variables that are this highly correlated are going to cause some serious issues with our regression coefficients going forward. So we'll keep that in mind as we go. I'll leave them in there for now so we can see how it affects things going forward. Now, miles traveled, X1, gas price, X3, no problems there. And then number of deliveries, X2, and gas price, X3, no problems there. So the only problem we have to worry about as far as multicollinearity goes is the correlation between the first 2 independent variables. So the quick summary. So the correlation analysis confirms the conclusions we reached by visual examination of the scatter plots. So we have some redundant multicollinear variables. So miles traveled and number of deliveries are both highly correlated with each other and therefore are redundant. Only one should be used in the regression analysis in the end. And we'll see how that all pans out as we build our model. We also have a non-contributing variable. So gas price is not correlated with the dependent variable at all and should probably be excluded right off the bat. Now, again, for educational purposes, I'm going to leave all 3 variables in so we can see how putting them in there affects the regressions we do. But in the end, it'll all work out, you'll see. Okay, so let's go ahead and get into some of our single variable regressions. Now in this first step, we will perform a simple regression for each independent variable individually. The first will be conducted in Excel, and then the rest in Minitab. That's what I prefer right now, but SPSS, SAS, Jump, R, etc. Are all fine as well. You can get them all to generate basically the same output. So depending on which one you use, you should be fine. But I'll be focusing on a little bit of Excel and the rest Minitab. We will discuss interpretations of the results we get from Minitab. And we will note how our results change. So we'll look at the coefficients in the regression. We'll look at the coefficient values, we'll look at their t-statistics, and we'll look at their p-values. We'll look at the ANOVA table in the regression. So we'll look at the f value and the p-value in that ANOVA table. We'll look and talk about the r-squared, the r-squared adjusted, and the r-squared predicted, and talk about what those mean. We'll also look at something called the VIF, or the variance inflation factor, and that's a statistic that Minitab produces that will help us weed out multicollinearity. And we will also talk about something called MALO-CP. That is a statistic that Minitab outputs that will help us pick the best model in the end. So let's go ahead and look at our first regression. So we're going to regress travel time y, which is our dependent variable, on miles traveled, which is our first independent variable. And here are our results from Excel. So we basically have three tables here. The first one in the top left are our regression statistics. Now in this case, multiple R is the same thing as our correlation. Since we only have one independent variable, they're the same thing. So 0.928, etc. is the same as the correlation we had a couple slides ago. Now R square is the proportion or percentage of variation in the dependent variable accounted for by the independent variable. So we can look at it as a percentage. So 86.15% of the variation in the dependent variable is accounted for by the independent variable. That's pretty high. Now the adjusted R square, that's the same thing as the R square, obviously. It is just adjusted for the number of independent variables in our model, which in this case is 1. So it will always be lower than the R squared, and how much lower really depends on the specific circumstances we're in. So the next number is the standard error of the regression. This is one of my favorite numbers, but unfortunately, most people don't know how to use it, or don't use it, or just skip it, or whatever else, but I think it's very helpful. So the standard error of the regression is the average distance of the data points from the regression line in dependent variable units. What we're saying here is that the data points are on average 0.342 hours away from the regression line. It is in the units of the dependent variable, and it gives us a measure of how tightly around the regression line our data points are. So it kind of forms a channel or a band around the regression line, and the narrower that is, the more tightly our data points are around the regression, and the wider that band is, the more scattered they are from that regression line. So the standard error of the regression tells us, relatively speaking, how wide that band around the regression line is. And it's also helpful because it is in the units of the dependent variable, in this case, hours. And of course, we have 10 observations. That's pretty self-explanatory. Now the ANOVA table, that gives us the significance of the overall model. So we have an F statistic there of 49.768, etc., with a p-value of 0.0001. That, of course, is significant. So the overall model here is significant. Now at the bottom, we have some of our coefficient information. Now we're interested in the miles traveled coefficient. So under coefficients, we have 0.0402. That is the coefficient of our miles traveled. And again, that is in hours. So what we're saying there is that for every mile that's increased, the time traveled increases by 0.0402 hours. Then we have the p-value, which is 0.0001, so we know it is significant. Now, if you notice, in this case, the p-value for the miles traveled coefficient is the same as the p-value for the ANOVA. And that's because we only have one independent variable. So how can we use this information? Well, we can take our coefficient information at the bottom and generate our regression equation. So we have an intercept of 3.1855, and again, that's rounded up here at the top, plus 0.0403. That is our coefficient for miles traveled down here at the bottom. And then times the miles traveled. That's our independent variable. That's our x1. So we have 3.1856 plus 0.0403 x1. where x1 is miles traveled. So what does that mean? An increase in 1 mile, so miles traveled x1, so 1 mile, will increase delivery time by 0.0403 hours. And that's how we can interpret the coefficient in this simple regression. Now let's go ahead and make a rough prediction for miles traveled that's sort of within the range of our original data. So we'll pick an 84-mile trip estimate. So we go ahead and substitute 84 in for our x1. That gives us 6.5708 hours. So that's a very rough estimate of how long it would take for an 84-mile trip. So 6 hours and 34 minutes. But remember, this is just an estimate. So it's going to have an interval around it. It's going to have some error around it. Now we can go ahead and find that prediction interval using some things we already know. And again, what I've done here is a very rough sort of estimate. Minitab can give us exact numbers, but a rough estimate of the prediction interval for an 84-mile trip. So we have 6.5708 plus or minus 2.31. Well, where do I get 2.31? That comes from our t distribution, our t table. So in this example, we have n minus 2 degrees of freedom. So that's 10 minus 2 in this case, because we have 10 observations. So we go to our t table, we look at degrees of freedom of 8, then we look down the table for a 95% interval, and we have a critical t of 2.31. That's where that comes from. And then we have 0.3423. Where does that come from? Well, that's my magic number over here on the left, the standard error of the regression. So this is very much like any other interval we calculated back in interval estimation. So we have a point estimator, so 6.5708 plus or minus the t alpha over 2, which is 2.31, times the error, which in this case is 0.3423. I don't expect you to sort of get this right now, but I just want to show you sort of how we use what we have here. So that creates an interval of 5.7764 to 7.3615 hours, or 5 hours 47 minutes to 7 hours and 22 minutes. That's our 95% prediction interval for an 84-mile trip. So again, that's sort of a step forward, what we're going to do in future videos, but I just wanted to quickly show you how we can use the information we get from a regression to make some rough predictions for other values. So here is our second one-to-one regression. So we have our second independent variable, number of deliveries, and our dependent variable, travel time. And this comes from Minitab. Now obviously it looks a little bit different. Now I will say that one of the best skills to have if you're doing statistics or whatever else is to be able to use really any software package, or at least look at the results of any software package and know how they correspond to each other. So in this case, the F value of 41.96 that's along the regression line is the same F value we had in Excel in the previous slide. So we look at the regression line going across, we have an F value of 41.96 and a P value of 0.000, so we know that's significant. Now at the bottom, we have the model summary. So S is the same thing as the standard error of the regression that we had in Excel. So here it's 0.368091. Then again, we have R squared, we have R squared adjusted, and then we have, in this case, R squared predicted. So this is an addition that Minitab gives us. And R squared predicted is basically how well our model does at predicting additional data points. So we'll talk about that more as we go, but R squared is really about predictive power. So here are our coefficients. So again, this looks very similar to what we had in Excel. So we'll look at the number of deliveries row. So we have a coefficient of 0.4983. We have a t value of 6.48. Its p value is 0.000, so we know it is also significant. The VIF we'll talk about later. And then the regression equation, which is really nice about Minitab and other software packages, it actually gives us the regression equation. So we have 4.845, so that comes from the constant coefficient up there at the top, plus 0.4983, that comes from the number of deliveries coefficient up there, and then we multiply that by the number of deliveries we actually have. So an increase in one delivery, one additional number of deliveries, will increase delivery time by 0.4983 hours, or almost a half an hour. Again, that's how we interpret a simple regression coefficient. So let's go ahead and make a rough for delivery estimate. Now we're not going to do the prediction interval again. We'll just do the for delivery estimate. So let's say a trip has 4 deliveries. So we can go ahead and substitute the 4 into our regression equation, and we come up with an estimate of 6.838 hours, or 6 hours and 50 minutes. So if we come into work one day and we have a trip with 4 deliveries on it. So based on our data, the best estimate we have is a trip of 6 hours and 50 minutes. So finally, here's our last single regression. So gas price X3 and travel time Y. So we go across the regression line here. We have an F value of 0.62. That's very low. Then we have a P value of 0.455. That is not significant. That's obviously not below 0.05. So that basically confirms what we looked at in the scatter plots and correlations. And that is that gas price really has no relationship or no linear relationship to travel time. Now, if we look down at the model summary, we have a standard error of regression of 0.886 hours. That is a huge standard error of the regression. We have an R squared that's 7.14%. Why even bother? The R squared adjusted is literally 0, and the R squared predicted is literally 0. So we know that this variable is really a dud. So here are our coefficients. We have the gas price coefficient of 0.81. We have a T value of 0.78, very low, obviously. P value of 0.455, same thing as we have in the F value above, the P value up there. We know that's not significant. The regression equation, why even bother? This is really not worth exploring any further. We know that gas price is really not a variable that contributes to travel time. Let's go ahead and summarize these 3 models. So in the first line, we have the case where we're only using our first independent variable. We had an F of 49.77, a p-value that's very low, significant, less than 0.001. We had a standard error of the regression of 0.34230. We had an R squared of 84.42 and an R squared predicted of 79.07. Now, I did that in many tabs, so we had it. But that's the actual R squared predicted that was produced. And then in the second case where we had the second independent variable, we had an F of 41.96, p-value less than 0.001. Now here we had a standard error of the regression of 0.36809. So remember what I said. What does that tell you? Well, in the first case, in the top row, on average, our data points were 0.34230 hours away from the regression line. In the second case, they were 0.36809 hours away from the regression line. So which model has data points that are more clustered in around the regression line? Well, the first one does, because its standard error of the regression is lower. Now the R squared adjusted for the second one is 81.99. It's a little bit lower than the one at the top. And then the R squared predicted is 70.27, which is quite a bit lower than the one at the top. And then finally, we sort of have our dud, our no good one, where we're using X3. I'm not even going to go through that anymore because it's obviously no good. So if we look at this example where we're only using one independent variable, which one do you think is the best? Well, I would have to say that the first one's the best. We have the highest F statistic, we have the lowest standard error of the regression, we have the highest R squared adjusted, and we definitely have the highest R squared predicted. So of these 3, the first one is definitely, I would say, the best. So let's do the case where we have 2 variables. So now we're going to put two variables in at a time. So we'll put x1 and x2 into the regression, we'll put x1 and x3 into the regression, and we'll put x2 and x3 into the regression. So this is a subset of two variables, but the interpretation is basically the same.